In this lecture, I'm going to give the proof for the implicit function theorem. But before that, let us define implicit functions. Here's the definition. Let's say we have an equation of x and y, which we write as f of x and y. And then a univariate function, phi of x, is said to be is an implicit function of this f xy equal to 0 if f of x and phi of x is equal to 0 for all x in the domain of this function phi. We don't need it. Okay, so this is the definition. So first of all, in this lecture, we only consider two variable functions, okay? Not 3 or 4 or many variables, only two variables. Okay, here's an example. Suppose we have a unit circle. So the equation for the unit circle centered at the origin is given by this. So this equation corresponds to this this equation. Okay, for this one, let's say we have an open interval on the x-axis from -1 to 1. Then we can define this function phi of x as square root of 1 minus x squared on this interval. So in this case, this is an example of an implicit function for this equation. And of course, alternatively, we can define another implicit function, let's say phi of x. Instead of positive square root, we can take negative square root of 1 minus x squared on the same domain. This is another example of an implicit function. So if we have a unit circle like this, the first, this one corresponds to this function, and the second one corresponds to this function. Okay, and we exclude endpoints here. Now the question is, when we are given some equation of x and y like this, when or where does an implicit function exist? So this question can be answered in some way by the implicit function theorem. Implicit function theorem. It goes like this. So let f of x and y be a function. Let's see, function of class C1 on an open region U in the two-dimensional plane. Okay, and let's see, say point P, a point, in U, in this open region, satisfies the following conditions. So first, f of AB is equal to 0. So this means this point is on this curve. on the curve defined by f of x, y equal to 0. So AB is on the curve. You should understand that this equation represents a curve in two-dimensional space. And second, FYAB is not 0. So this means partial derivative of the function f with respect to y. Okay? If this derivative is evaluated at this point P, then it's not 0. So suppose these two conditions are met. Then there exists an open interval I on the x-axis such that A belongs to this interval, and also a function phi of x on this interval such that the following two conditions are met. F of x phi x equal to 0 for all x in the interval. So this means this phi of x is an implicit function of f of xy. And condition B is equal to phi of A. Okay, and furthermore, this function is differentiable on this interval, and we have its derivative as negative f of x phi of x. So this is the partial derivative of f with respect to x divided by partial derivative of f with respect to y. From the given condition, this denominator is not 0, so this makes sense. Okay, so this is the statement of this theorem, the implicit function theorem. Let's see what this means. First of all, we assume that this function f of xy is of class C1. So this means this function is differentiable with respect to x and y at least once, and the derivatives, partial derivatives, are continuous. Okay, so that's what this means, C1. Okay, and it's defined on open region. So open region is a subset of this plane in this case, and it is a connected region. Okay, it is connected, path connected subset, and P is a point in U. So we have this. So AB, this point P is on this curve defined by f of xy equal to 0, and the partial derivative with respect to y evaluated at AB is not 0. Okay, so let's try to prove it. First of all, since by the given condition, since FYAB is not 0, so this means this differential coefficient is either positive or negative, right? So this is either positive or negative. In the following, we consider only this case. And the case for this one, negative case, is very similar. So we just omit it. Okay, and we are going to prove in 3 steps. First, we derive or define. Let's say define. Define this implicit function. And second, we prove that this is continuous. And 3, we prove that this is differentiable. Okay, so let's do it. Okay, let's do step 1, where we are going to construct the potential implicit function phi of x. So how do we do that? First, since fy, by assumption, fy of ab is positive, and since f is a C1 function, so fy of xy is continuous. So we can find there exists epsilon that is sufficiently small such that if x minus a modulus is less than epsilon and y minus b is less than 2 epsilon, then fy of xy is also positive. Okay, so this means if the point xy, this point is sufficiently close, close to point AB, then this partial derivative is also positive, because this partial derivative is positive at AB. So if xy is close enough to AB, then this is also positive. So I hope this makes sense. Okay, then let's say x0 is in this interval, a minus epsilon to a plus epsilon. So for all x0 within this interval, define function g of y as f of x0 and y. So we fix the value of x, then regard this as a function of y. Okay, then on this interval, b minus 2 epsilon, b plus 2 epsilon, this comes from this condition. We have the derivative of g with respect to y is equal to fy of x0 y, which is positive. This epsilon is so small that this holds. So in this case, x0 is in this interval and y is in this interval, so this is positive. So what this means is that this function g of y is strictly monotone increasing. Okay, because derivative is positive, strictly positive. So in particular, we have, from the given condition, this f of AB is 0. Remember, this is one of the conditions in the theorem, this one. So let's see. So this means, and also this is strictly monotone increasing. So this means f of a b minus epsilon. So this one should be negative, and f of a b plus epsilon should be positive, right? So this b minus epsilon is a little bit less than b. So at this point, it should be negative because at a b, exactly b, it's 0. And similarly, this should be positive. Next, we want to generalize these results to some neighbor of a. Okay, so these inequalities hold for exactly at a equal to x equal to a, right? But we want to loosen this condition so that not just exactly at a, but neighbor of a, we want to have these inequalities. So that is actually not so difficult. Again, since fy x, wait a minute, x y is continuous. Again, so we can find a sufficiently small epsilon prime. So sufficiently small. Such that if x0 minus a is less than epsilon prime, then we have this function. It's a function of y is strictly monotone increasing. And f of x0 b minus epsilon is negative, and f x0 b plus epsilon is positive. So again, this is continuous function. So if x0 is sufficiently close to a, then again this is monotone increasing because sorry, this is no 0 here. F of x0 y is strictly monotone increasing function of y. Okay, because fy x0 y is wait a minute. Yeah, this is positive. Wait a minute. So yeah, this is positive, so it's monotone increasing, and also so since x0 is sufficiently close to a, and f, as we have seen, f of a b minus epsilon was negative, so if x0 is close to a, sufficiently close to a, then it should be also negative, and same for this one. Now we use the intermediate value theorem. So by intermediate value theorem, for each, let's say, use quantifiers, for each x0 in this interval, so sufficiently close to a, so that means these two conditions are met. So for each x0 satisfying these two conditions, in other words, then there exists some y0 in this neighbor, because this we have these values here. So there is some y0 in this interval such that f of x0 y0 is equal to 0. And moreover, such y and such y0 is unique. Why? Because this function is strictly monotone increasing. It's a strictly monotone increasing function of y. So if this function crosses this one, 0, then that y0, the value of y0 must be unique. So there is only exactly one value of y, that is y0, that satisfies this equation for each x0 in this interval. Okay, so in this way, so in this manner, we can make correspondence. x0 maps to y0, right? So if we pick x0 in the neighbor of a, then we can determine a unique value of y0 satisfying this equation. So this defines a function. So this function is this mapping is defined to be that phi of x. Okay, so this is a function defined on this interval. Let's call this I. Okay. So this is how we define or construct the potential implicit function. And that was step 1. Now let's do step 2. In step 2, we show that phi of x is continuous. And phi of x is, of course, the function we have defined in step 1. So what we need to do is to show that for all x0 in I, of course, this I was that open interval, which is the neighbor of A. Okay, for all x0 in this interval, phi of x0 plus h converges to phi of x0 as h approaches 0. So this is what we want to show. Okay, and we prove this by contradiction. Okay. Contradiction. Okay, so suppose phi of x is not continuous. So that means limit h approaches 0, phi x0 plus h is not equal to phi of x0. So yeah, if we restate this statement in another form, it's like this. So this means there exists some sequence, let's say hn, and also there exists some positive number epsilon double prime such that hn converges to 0, and for all natural numbers n, the difference between phi of x0 plus hn minus phi of x0 is greater than or equal to epsilon double prime. So this is another way to state this fact, this assumption. Okay, so by construction, so this means due to the way we constructed the function phi, we have for all natural numbers n, phi of x0 plus hn, this is bounded in this range, in this interval, b minus epsilon to b plus epsilon. Okay, and of course, since hn is a sequence, phi of x0 plus hn is also a sequence of real numbers. Okay, and it is bounded. So by the Bolzano-Weierstrass theorem, Bolzano-Weierstrass, we can find a subsequence. There exists a subsequence of hn. Let's say hnk, so subsequence, such that limit k goes to infinity, then phi of x0 plus hn k converges to alpha. So if in case you forgot, the Bolzano-Weierstrass theorem says if a sequence is bounded in a closed interval, then it contains a subsequence that converges to some value within that interval. Okay, so this alpha belongs to this interval, b minus epsilon to b plus epsilon. Okay. However, this function phi is not continuous, so this means by this condition, wait a minute, this condition, we have, let's see, phi of x0 plus hnk minus phi of x0. Its modulus is greater than or equal to epsilon double prime for all k. And also alpha minus phi of x0 should be greater than or equal to epsilon double prime. And of course, from this, we can say that alpha is not equal to phi of x0 in particular. Next, consider a sequence of points on two-dimensional space. That is these points, x0 plus hnk and phi of x0 plus hnk. Okay, on this two-dimensional space. And this sequence converges to this point, obviously. So the way we chose this subsequence determines the limiting value of this as alpha. That's how we chose it. Okay, so Now f of xy is continuous. So f of, if we take the arguments of this function f as these points in the sequence, h and k, and phi of x0 plus h and k. So this function, this value converges to this x0 alpha. Okay, this one converges to x0 because hn is a sequence that converges to 0, and h and k is its subsequence, so it also converges to 0. Phi of x0 plus h and k converges to alpha because of the way we chose this subsequence. So by construction, it converges to alpha. Okay, as k goes to infinity. But for all k, we have phi f of x0 plus h and k, phi x0 plus h and k equal to 0. This is how we define the function phi. So this must be true. And so it's when k goes to infinity, then it must be true that f of x0 and alpha is also 0, right? And on the other hand, we also have f of x0 and phi of x0 is also 0, right? Because that's how we define this function phi. So this is satisfied and this is satisfied. So for a given x0, we have two values of y, that is alpha and also phi of x0, that satisfies this equation. Okay, however, if you remember this function, if any y0 where y0 is in this interval b plus minus epsilon, if this is 0, then this y0 is unique, right? Because this function f of x0 of y as a function of y was strictly monotone increasing function. So this means, now we have the same x0 here and here, but we have two different values of y. One is alpha, the other is phi of x0. So there are two values, but it must be unique. So that means alpha is equal to phi of x0, which is a contradiction. Because by assumption that this assumption, they cannot be the same. So in particular, where was it? Where was it? Yeah, so alpha is not equal to phi of x0, but we have this result. So it's a contradiction, and therefore phi of x is continuous. So that is the conclusion of step 2. In step 3, we show that this function phi of x is differentiable on the interval I. So that means we need to show that this limit exists. So h goes to 0 and phi of x plus h minus phi of x over h. So this limit exists. So that's what we need to show. Okay, so first, by Taylor's theorem, we have this finite Taylor expansion, f of x plus h, y plus k will expand to the 0th order, plus f partial derivative with respect to x. Let's see, x plus theta h and y plus theta k times h plus fy x plus theta h y plus theta k times k, where theta is a constant between 0 and 1. Okay, so let's set h to be not h, it's k. Let's say y to be phi of x and k to be phi of x plus h minus phi of x. Then we have f of x phi of x equal to f of x plus h and phi of x plus h. They are both 0 because of the way we constructed this function phi, right? So we have this, so we put this these into this Taylor expansion. Okay, so this part is 0 and this part is 0 if y is this, right? And k is this, so we just replace them. So we have, after all, f x x plus theta h and phi x plus theta k times h plus f y x plus theta h phi x plus theta k times k equal to 0. Okay. Now k is this. This k is this. So just replace them. And so we have, solving this for k over h, we have, let's see, k over h is equal to phi x plus h minus phi over x. So this is the definition of k here, and h, which is equal to negative f of x plus theta h phi of x plus theta k over fy, this one. Okay. Now from step 2 we know that this function phi, excuse me, phi is continuous. So this means k, if, okay, let's see, k converges to 0 as h approaches 0, right? Because phi is continuous. And also, f of x, fx and fy, so they are partial derivatives with respect to x and y respectively. They are also continuous because f is of c1. It's continuously differentiable. So if as h approaches 0, we have this one. This approaches fx and x phi of x over, and of course this left hand side is the derivative of phi with respect to x. So this proves that this function phi is differentiable, and the derivative is given by this. And the proof is done. By the way, this last equation, this one, can be obtained easily once we admit the existence of the function differentiable function phi of x. So if we have this equation, f of x and phi of x equal to 0, we can just differentiate both sides with respect to x. So if we do that, we have fx and x and phi of x plus, by applying chain rule, we have this and phi prime of x equal to 0. So if you solve this for phi prime, then we have this equation. Okay, same as this one, of course. By the way, in this theorem we had this condition. The partial derivative with respect to y evaluated at AB is not equal to 0. So this means if we have a curve on x and y plane, something like this. So if the slope of the tangent line is vertical, so then this means this derivative is 0. So unless this is vertical, we can always define an implicit function around this point. Okay, so for example, in this case, we may define an implicit function in this interval, for example. Right? So what if this is 0? Then what can we do? We can simply cannot define any function, or actually we may be able to define a function if fx ab is not equal to 0. So even if this is 0, if this one is not equal to 0, then we can define a function of y. So x as a function of y. So instead of this function, so instead of this, we can define x as a function of y. So just swap the roles of x and y, and we can prove the implicit function theorem for this type of function. Okay? So it's the same thing. But what if both this and this are 0? Then have we cannot do anything regarding implicit function. And such points, if AB satisfies these two equations, then this point is called a singular point. Non-singular points are called regular points. Okay, so if the point is regular, then we can define some implicit function, either of y or x.